Hi, I'm Emmanuel Lamarche, and this is my Lab 5 for Physics 2112. In this lab, one of our main focus was really Faraday's law and how induced currents from magnetic fields act on objects. So some of the main principles that we used on this was the gravitational force acting on the magnet, Faraday's law for the induced EMF from a changing magnetic flux, and then of course the magnetic flux, and then also the magnetic field, and then the magnetic force from that magnetic field, and also Newton's second law, all acting on this bar magnet. And so this experiment, how it worked was by using a roll of aluminum foil, drop the bar magnet through the roll of aluminum foil, and use a cell phone camera to record how long it took to fall through. And so based on 5 trials of that, the average time it took to fall through the tube was 1.2 seconds. And this graphic kind of shows an example of how the forces would act on the bar magnet and then with the tube around it. And so in GlowScript, we were able to use some of the data we collected about the size of the aluminum foil and the mass of the magnet to calculate the magnetic flux based on the field from the bar magnet using the magnetic dipole moment that I calculated in Lab 3. And then from this magnetic flux, we could calculate the induced current on the aluminum foil, treating it as a lot of small loops. And then from this induced current, we could calculate the magnetic force on the bar magnet. And so from the GlowScript coding, we saw that the computational prediction for how long it should have taken the magnet to fall through the tube was 0.967 seconds, which was a little bit shorter than when we actually calculated it. And the GlowScript also showed a model of the current and how it changed through the tube, and also the velocity versus time. So I'm going to try to play this because I thought it was really cool. Yeah, so that models the magnet falling through the tube and how that impacted the current, and then the velocity of the magnet as it fell through the tube and how it was impacted by the magnetic force from the induced current. And then some of the observations I made generally was that the magnet was falling slower in the tube than if it was falling in free space outside of the tube, which means that the magnetic force was opposing the gravitational force on the bar magnet, which we could kind of see in the free body diagram a few slides ago. And so some of the things that to consider for this about how this would change if the situation was a little bit different. If the resistivity of the conductor was reduced as close as possible to 0, this would mean that a much stronger current would flow throughout the tube, and this would mean that a stronger magnetic force would be induced and act upon the bar magnet. So the magnet falling through the tube would fall even slower than it did now. And if the resistivity was reduced as close as possible to 0, magnetic force could, in theory, oppose gravitational force completely. And another thing is if holes or slots were cut into the tube as the magnet was falling, this would kind of, in practice, reduce the number of loops through the tube because there'd be less aluminum foil, and so less loops going through it. So this would decrease the current for it, so the magnetic force opposing gravity on the bar magnet would decrease, and so the magnet would fall faster than if there were no holes or slots cut into the tube.